The turbine engine is an amazing piece of machinery. I mean, it is super high specific power and excellent energy density. It's very difficult to compete with a turbine engine in performance. The real advantage of going to hydrogen is that it gives you enough performance to do the missions that the turbine helicopters are doing, albeit at a higher weight empty fraction, but it does so at a operating cost that is like 50% lower because the turbine engine is such a high maintenance cost item and the fuel is such a high cost item. And in a fuel cell, there's hardly any moving parts. So we expect to be able to achieve 10,000 cycles on a fuel cell, roughly equating that to a turbine engine. It's substantially lower cost.
Hey everyone, and thanks for listening to another episode of DIV Innovators. Today I'm speaking with John Piasecki, President and CEO at Piasecki Aircraft Corp. John, thanks for chatting with me today.
Thank you, David. Happy to be with you.
Yeah, this is exciting. A lot of experience in the VTOL and drones and helicopters. So how did you find yourself here? I know your family has a legacy in vertical lift aviation. Talk to me a little bit about how Piasecki Aircraft begun and how you found yourself in this position.
Well, Piasecki Aircraft, its legacy goes all the way back to the beginning of the helicopter industry. My father, Frank Piasecki, was one of the original inventors of the helicopter, and he and some compatriots from Penn created one of the first helicopter companies, Piasecki Helicopter Company, which then evolved into VTOL, and they're probably most famous for developing their signature tandem rotor helicopter, which is in service today with the Chinook and was in service with the Marine Corps and the Navy for decades and around the world with the CH-46 and Model 107. So after he sold that production company to Boeing in 1960, he then spun out the research and development group into Piasecki Aircraft Corporation, the company that my brother Fred Piasecki and I run. And it's primarily had a focus on research and development, mostly for the U.S. Defense Department in the vertical lift and unmanned aerial vehicle sectors. I was sort of born into this world because being the son of Frank Piasecki, I was dragged to the office every weekend. We had to work in the office on Saturdays, and then Sundays was cutting down trees on what we called vine patrol at the house. So we all learned how to put in the long hours, and I was always fascinated about vertical lift and flight. Became a pilot when I was started training in high school, actually, and steeped in the history of it. It's always been fascinating to me that particularly with vertical lift, people who use vertical lift are doing really important things or very urgent things, and so the user community is really wonderful to work with because you feel like you're contributing to important needs. So interestingly, I was not planning on making this a career. My dad was kind of sneaky. He asked me to come help him right after college. I was like, "Well, Dad, I'm going to business school. I'm not going to be able to do that." And he said, "All right, well, just for a little while." And I did that, and I was just amazed about how many cool ideas that really deserved to be exercised and considered and deployed to the warfighter weren't making it past the front gate because, the system, for a variety of different reasons, really was not very friendly to innovation. And it sort of upset me. I felt like we drifted from our roots in the country for, being famous for bringing new ideas and new ways of doing things to bear. The system was getting ossified. And so I sort of took that as a challenge, and I've been fighting that battle with my brother Fred for a long time.
You're fighting on the same side or fighting with him, against him?
No. Well, we do have our fights. We're like yin and yang. We're different animals. But no, I mean, the two of us have worked together closely for 35 years, trying to develop innovative solutions to difficult problems and in transition technology. So it's been a wonderful career so far, and we've got a lot more to do.
That's great. business, family business. It's tough for those to continue to survive over generations. So I applaud you, your family for.
Yeah, I know the odds are stacked against us, but we love what we do, so it makes it
Yeah.
easier.
Yeah, you got a great mission, that mission. Well, how have you seen, that if you bring up an interesting point, obviously, late 50s, 60s, into the 70s, lots of innovate. I mean, planes could be ginned out, F-15s, F-16s. So you go back to the Century series, putting out aircraft. Why do you think that slowed and stopped? And then how has that changed over the last, 15, 20 years, or maybe the last 5?
Well, the rapid developments of the 60s, 50s and 60s was I think important in terms of exercising new ideas to solve problems, particularly in the military world. The Army did a whole bunch of VZ programs that were looking at everything across the board. And I think that informed their decision about what was most practical. And once they selected, the conventional helicopter to do most of their needs, and certain platforms became what I'll call incumbents, the life of these helicopters is 20 plus years, and once you do, the industry's constantly upgrading their aircraft. So rather than developing new aircraft, you found that it was easier for the services really just to upgrade what they had rather than going through the whole battle of new competitions. And the necking down of the industry really sort of eliminated a lot of competition. And you, of course, have the OEMs who, quite understandably, are very defensive of their programs. And all of those factors combine to make it a very high bar to penetrate that industry. And that has changed definitely over the past 10 years, and even more so over the past 5. There's been a recognition that, well, I think within the customer community, within the Defense Department, that they can really leverage small business to develop innovative ideas much more rapidly, much more economically than these huge contracts with, the large OEM type companies, where it's very expensive it's almost like you can't afford to meet a good idea. And so I think the department has turned towards small business, particularly in these areas like unmanned aerial vehicles, where the cost structure of the smaller companies allows them to do the work at a much, much lower cost and much more rapidly, because they don't have bureaucratic hurdles internally within these companies to slow them down. So there's also been a shift within the customer community that's really looking for companies to develop their own products to a certain level of maturity before they're further developed or acquired by the department. That puts a big strain on small companies because most of them are undercapitalized. And so, that is an area, I think, that from a policy perspective, the department needs to look closer at. They did establish a program called the Small Business Innovation Research Program, which I think has been hugely successful as planting seeds. But the problem with that program is it gets you to a certain point where you figure out your idea has a chance of working, but then you fall into that classic valley of death to get it to a practical demonstration and transition into a program of record. So I think there's some work that needs to be done within the department and across the industry in terms of how do we get good ideas transitioned into practical application.
Yeah. Well, with you, it sounds like you're more focused on the R&D side, right? Of really just kind of creating ideas and getting them maybe to that point.
Yes.
And then is your business model then to take that and then to get it in program record and then go into production, or you sell that then to maybe a different OEM? Or
yeah, our business model is one where we will identify a problem that needs to be solved that's within our sphere and come up with innovative ideas about how to do it, and then we will engage the customer. Either we'll initiate something, or there'll be a solicitation that comes out that's talking about the problem, and we'll go through a series of smaller contracts that do feasibility studies and design trades and all that, and then we get to a point where you got to start validating key enabling technologies and ultimately go to flight. And we're really good at that. We take things from an idea to breaking the southerly bonds of Earth on a regular basis. We have 4 flight demonstrations programs that will be going on over the next 6-7 months. Where we are challenged is in the transitioning of technology, and that's a capital challenge. We will often work with universities and large OEMs. I've got experience in both areas. We did a lot of work in autonomous flight early on in the 2000s. And for example, with Carnegie Mellon, we developed the first guidance, navigation, and control LiDAR-based system for autonomous flight. And it was the first man-rated helicopter autonomous flight back in 2000, I think it was 10, with Carnegie Mellon. And that team then spun out and created a new company. So that's an example of enabling technologies that we developed, then transitioning. Some of the other types of programs and relationships we've had to support transition are working with large OEMs. We've had multiple programs with Lockheed Martin in the UAV space and with Boeing, either them as a sub or us as a sub. We have not as yet transition one of those major programs into a program of record. It's a difficult challenge. So we've got more to do. We acquired Sikorsky's production facility in Coatesville called the Heliplex 2 years ago, and that move is really part of a strategic shift on the company to move beyond just the R&D side and get into production and have the capability to do it organically rather than relying on OEMs.
Oh, that's great. And so you mentioned you were in, unmanned, and then sounds like you're more in a vertical lift. Can you talk to me about, what are your, I'd say key solutions that you're working on right now to solve problems, on a platform basis or even just a technology basis?
Yeah. So there are 2 really dominating environments that are driving our innovation. The first is the lethality of the warfighting environment, like we've seen in Ukraine. It has gone asymptotic, and manned air platforms are extremely vulnerable to threats. And being able to support combined maneuver operations with manned helicopters is a big challenge. And all the services are moving to what we call distributed operations, where in order not to have a concentrated collection of troops in one space that's vulnerable to attack, they're splitting it up into small mobile units and they're disaggregating, and then they maneuver to a position of advantage, and then they reaggregate, strike, and then disperse. And in order to do that effectively, you need a lot more vertical lift, and not only to move people, but to also resupply these small units. And they can't afford to take on 10,000 pounds of supplies, because then they can't move. They'll be just sitting there guarding so they need much more discrete, high sortie rate resupply. And so logistics in a contested environment is really a core focus of ours. The other area that we are really focusing on is Indo-Pacific, and the paradigm shift that really is driven by that operating environment is this huge expanse of sea and longer ranges, and therefore longer response times, connectivity between distributed forces, all is putting a major stress on aviation in general and vertical lift in particular. And so coming up with configurations that frankly can have performance that goes well beyond conventional helicopters is going to be an important part of being able to effectively operate in that kind of environment. So that's those two things, those two operating, Ukraine and Indo-Pacific are the 2 dominating features. So when you look at our portfolio of programs, we have configuration technologies like compound helicopter technology, which augments lift and thrust of a conventional helicopter in order to achieve higher speeds and more survivability and reduce life cycle costs. And other configurations like tilt-duct configurations that are capable of being compatible with tilt-rotor technologies, super high speed for vertical lift and longer ranges, and the ability to support operations over an extended battle space. And then in terms of enabling technologies, we're working on adaptive flight control, which when you have these advanced VTOL configurations where you have a certain level of redundancy in lift, thrust, and control, adaptive flight controls allows you to mix those effectors in order to achieve a variety of different objectives, whether it's optimizing your performance, maximizing your maneuverability, or minimizing vibration fatigue loads that drive life cycle costs. It gives the pilot another degree of control over the aircraft and how it's used in order to maximize its effectiveness. So that's a very cool area. It's a challenge because it's non-determinative flight control, which freaks out the airworthiness certification authorities because they like to have a very defined relationship between a stick input and a control output. So a lot of R&D is going into how do we do this, but in a way that's certifiable from an airworthiness perspective. Another really cool area is hydrogen fuel cell propulsion. There is, hydrogen is a unique potential fuel because you can make it anywhere as long as you've got water and energy. And when you look at the composition of resupplies that are deployed to these units, something like 70% is fuel and water. And if you can reduce the amount of material that has to be transported to these smaller units, and they have an organic capacity to generate their own fuel, that's a game changer. So in the VTOL world, there's been a lot of investment in batteries for electric VTOL applications, mostly focused on commercial urban air mobility missions. But for a lot of the military missions, batteries simply don't have the energy density. So we got involved with hydrogen fuel cells, specifically high temperature proton exchange membrane fuel cells that don't have all the infrastructure required that low temp does, things like humidifiers and water management systems, et cetera. So they're lighter for a given amount of power. So they're higher. They've got higher specific power, and then that gives them the ability to have higher energy density, maybe 5 times the energy density of batteries, and maybe 2-3 times the specific power of low temp fuel cells. So that's an area. We are also working things like additive manufacturing. We've got teammates that are trying to establish the pedigree to apply additive manufacturing to flight critical elements that are very long lead currently. A good example of that is like gearbox castings. It is very difficult to get a gearbox casting in less than 12 months. And then when you do, you've got to build like 12 of them because half of them are not going to fail the exit, inspection. And so additive manufacturing could help development because it could shorten the overall development time for dynamic components, but it also, I think, is going to have benefits in affordability when appropriately applied. So that's just a smattering of different enabling technologies that we're working on. And each one of them, we try to take to a level of maturity where there's objective evidence of efficacy so it can transition to the next stage.
So let's just take hydrogen, for example. You're doing the fuel cell production. Are you incorporating that into then some of your platforms like your tilt-duct or?
Yeah, so we go through a crawl, walk, run development path where if you take the hydrogen fuel cells, we've done a lot of work with our partner Zero Avia in the basic technology in the lab in terms of both the chemistries and the mechanical aspects of the hardware in order to meet certain level of performance capabilities that are exit criteria. And we'd put it through tests, and then we refine it through several iterations. Once those cells are graduated out of the lab, they'll then go into what we call proof of concept demonstrator. We acquired a off-the-shelf light helicopter, small light helicopter, that we've taken the engine, the internal combustion engine out, and we've replaced it with an electric motor and the fuel cell stacks and the balance of plant. And we'll fly that this year to demonstrate initial demonstration of capability. And a really useful tool to learn on, right? So it's we're not building a huge aircraft. It's a small, test bed that, frankly, is a method of getting the engineers to really learn and appreciate the challenges involved with that technology's integration on an aircraft. And that is then the stepping stone for the development of a full-scale propulsion system, 660 kilowatts. And that is the core of a new product called the PA-890, which we're hoping will be a real disruptor in the commercial helicopter markets, capable of doing a lot of the turbine helicopter missions, but at half the cost.
Yeah, I'd like to come back to the PA-890, but if you take what you envision, we haven't done it yet, but a combustion engine helicopter device, a hydrogen. Talk to me about, where the pros and the cons exist. There's a logistical, advantage potentially of how you get fuel and what type of fuel. But as far as range, the ability to carry fuel on the aircraft, what are the pros, cons, distance, speed?
Yeah. So the turbine engine is an amazing piece of machinery. I mean, it is super high specific power and excellent energy density. It's very difficult to compete with a turbine engine in performance. The real advantage of going to hydrogen is that it gives you enough performance to do the missions that the turbine helicopters are doing, albeit at a higher weight empty fraction. But it does so at a operating cost that is like 50% lower, because the turbine engine is such a high maintenance cost item and the fuel is such a high cost item. And in a fuel cell, there's hardly any moving parts. So we expect to be able to achieve 10,000 cycles on a fuel cell, and that roughly equating that to a turbine engine, it's substantially lower cost. And the energy density of hydrogen is extraordinary. Its big challenge is its volumetric energy density. And so we're looking very closely at cryocompressed and liquid hydrogen as a means of providing fuel on the aircraft. And of course, all of that is very aircraft centric. It needs to be tempered by the challenges of infrastructure. And traditional aviation already has a well-established fuel distribution and consumption infrastructure. That does not exist yet for hydrogen. There's plenty of hydrogen around. It's been being produced for industrial purposes, but the distribution network to support aviation needs to be implemented, particularly if you want green hydrogen, which a lot of people who are interested in hydrogen are interested in the fact that it's got zero emissions. And so that is, we have to work that issue in parallel with the development of the aircraft and the power system.
So if I heard you right, the real advantage then is going against, I'd say, more of the unmanned vertical lift, smaller, like go against battery powered.
No, well, in terms of performance, it's well beyond battery capability. You also have to appreciate that, when you install a battery on an aircraft to give you a certain amount of performance, if you want to extend that performance, you have to add a whole nother battery, right? Whereas with hydrogen fuel cells, once you put the infrastructure in for the hydrogen fuel cells to convert hydrogen into electricity, you have a marginal amount of additional weight for additional hydrogen. It's de minimis relative to a battery where you have to add a whole nother mass of to contain the energy. So that's one thing. And the hydrogen fuel cell technology is rapidly evolving, and it's not going to beat the turbine engine. But the technology challenge to us is to make it good enough relative to the turbine engine.
Yeah, and if you reduce the life cycle cost, the operational cost, there's definitely advantages.
That's the main thing. It's the main thing blocking the broader use of vertical flight mobility is cost.
And so the PA-890, talking a little bit more about that and where it is in its journey.
Well, the PA-890 is a slowed rotor wing compound. So the aircraft configuration is designed to unload the rotor with a lifting wing and provide propulsion with auxiliary thrust device. So basically, you're combining the best attributes of a helicopter with an airplane. and it retains one really important feature, particularly for commercial operations and FAA certification. It retains the low disk loading rotor. So if you ever are in a power out situation, you have the ability to auto rotate to the ground, which is a key requirement of both Part 27 and Part 29. It's not quite as high performance as more exotic configurations like tilt rotors, but it's substantially better than the conventional helicopter. So by combining slow rotor wing compound with the hydrogen fuel cell, we're confident that we can deliver a mission capability to to the operators that meets their requirements that are currently being satisfied by turbine helicopters, and do so at half the cost, zero emissions, and reduced noise.
That's cool. I want to go back also the tilt duct. Talk to me a little bit about that because that seems pretty cool. Is that your ARES? Is that what you're calling the aerial?
Ares?
Ares.
Yeah. Yes. The Ares is a flight demonstrator that it's a proof of concept platform that will validate the tilt duct configuration and its flight control laws, et cetera. It's had its first flight and it's going to be going through envelope expansion tests this summer. And, when you design a new aircraft, you got to connect dots, right? In terms of its capabilities in order to be valuable to the customer. And so the first thing was a small footprint, something that can fit in a small deck ship hangar or inside a C-130 so that it's got mobility within the operating area. The second feature was that the mission profiles that are out there today, both in the Marine Corps and the Army, are dramatically extended distances over traditional operations. So, the Marines are flying missions with the V-22 that are like 300 nautical mile radius. And so when you have missions like that, you need to move beyond conventional helicopter dynamics because you need the efficiency of being on a wing with higher propulsive efficiency available with a thruster. And so that's important. And then when you get to your objective, if you want to be supporting these small distributed units, you need to have a small landing footprint so that you can deliver whatever it is you're delivering or recover whatever it is you're recovering, as close to the small unit as possible. And ultimately, we were talking earlier about the fact that these small units need to maintain their mobility. So it's got to be right-sized for small unit resupply and support. And then another attribute is modularity. So, sometimes it's just as simple as resupply, so you need a cargo module. Sometimes they've got wounded, and you got to be able to CASEVAC wounded out. There are other missions like close air support or ISR. These are all functions that would be very useful to be able to support small unit operations that otherwise might not have available if they've got to call back, to 2 echelons up and ask for help. And so multi-mission capability was an important part of the overall design concept. And then, of course, autonomy is a key enabler. So when we added all those things up, that was the genesis of the Ares concept. It's a ducted tilt duct vehicle, so it's compact, can generate a lot of lift in a very small footprint. It turns into an airplane as the tilt ducts tilt forward. So it's got speed, it's got range. When it gets to its objective, it has VTOL capability with a small footprint. The ducted fans protect personnel around the vehicle, and it's right sized to meet the small unit needs. And it can be used for a lot of missions, logistics, combat support, et cetera.
And how big do you envision this vehicle?
So the Ares demonstrator is about a 7,000-pound gross weight vehicle. The design studies we've done for the Marine Corps and other DoD services, those mission requirements are sizing the aircraft out to about 14,000 pounds.
And would this be a complement to, like the CV-22s or the FLRAA,
Oh, yeah. It's exactly the kind of capability that I think is needed to support V-22s and the FLRAA platform, because the conventional helicopter support aircraft that are operating with those platforms can't keep up. They don't have the range. and they're all manned platforms. So I think, the FARA program that was supposed to go hand in hand with FLRAA was terminated by the Army. And I think one of the contributing factors, I might be wrong, but I think one of the contributing factors was that the speed and range of that platform was not equivalent to FLRAA. So you were acquiring a whole new fleet of aircraft that couldn't support the other fleet of aircraft that you were acquiring. So I think that there is going to be a need both in the Marine Corps and the Army for something like Ares that can do a lot of different things and be compatible.
Are you seeing a demand signal from them that looks like they're going to move forward with this, or are they still toying around with ideas and, small?
I think they're looking at a lot of different ideas. The Marines did come out with a requirement in 2000, I think it was 18, a JROC approved requirement for a thing called MUX, MAGTF Unmanned Expeditionary Vehicle, that had 7 different missions it wanted to be able to do. Unfortunately, the technology wasn't, we hadn't flown yet, and the technology wasn't out there. So they split that requirement up, and they took the long range, long endurance, persistent missions, and they bought some, I think, Reapers or fixed wing UAVs to satisfy those requirements. And they're now swinging back around and looking for vertical lift solutions to support logistics in a contested environment. Interestingly enough, logistics in that MUX requirement was like the lowest priority. Now it's the highest priority.
Yeah, that's
somebody got wise. And so I think there's a real need on the Marine Corps side for something.
If we fast forward 10 to 20 years, what does military and even commercial rotorcraft, what does it look like, and what are those, are there any other technologies you see going into vertical lift that haven't really been fully vetted out?
I think there's always going to be a role for the conventional helicopter, but there's going to be a whole nother level of performance of VTOL platforms that sits, above helicopters, but not as expensive as F-35. There is space there for platforms that have the capability to address some of these long-range needs. And once you deploy a system like FLRAA, all the other systems have to be able to match it, because you can't deploy your warfighters and then not support them. That's going to result in a whole bunch of innovations that have to come along. On the commercial side, unfortunately, I think that there's been too much hype in the battery-powered eVTOL sector, and I think frankly, there's going to be, a lot of money's been invested, something like $10 billion. I've heard as much as $30 billion. For short-range missions, batteries are perfectly fine. But for these longer-range missions, if you're going to penetrate into the regional air mobility instead of just the urban air mobility, you're going to need more capability. And so that's why I think hydrogen fuel cells are a big part of that. The autonomy is also a major feature. And it's not just for unmanned operations, also for piloted aircraft in terms of a pilot tool. If we're going to broaden the application of vertical lift mobility, the availability of pilots is a big issue. And I think in 10, 20 years, the autonomous flight controls are going to enable operators that are not necessarily pilot-rated operators, that are more in a supervisory control capacity rather than stick and rudder, which in some cases takes away the joy I have with flying, but it opens up the role of operator to somebody who's more like a mission manager than a stick and rudder pilot. So that's a major thing. There is an area that I think is ripe for exploitation. There was a great paper that was put forward by Nick Lapos, who was chief test pilot for Sikorsky some years ago at the Vertical Flight Society. It was the Nikolsky lecture, and talked about a cyber-enabled rotorcraft. And there's a lot of overlap between that and the adaptive control program that I was talking about earlier. And it really is about how do you leverage software-enabled systems to expand what you can get out of your aircraft. We have, the traditional development of aircraft is driven by factors of safety that add margin to account for our ignorance, right? So you have structural factors of safety on one on top of the other, and all of a sudden, a widget that you're designing to do X it's a lot heavier because it has to have that margin of safety that's driven by ignorance. Well, if you can deploy software-enabled systems, both in sensors and computing and what have you, you can understand what the actual loads are that the aircraft is experiencing, and you can use the flight control system and the available effectors on the configuration to extract more capability without exceeding the limits, the true limits of the aircraft. And I think you could see somewhere, between 15 to 20% improved capability for a given weight. But I can see the technology. What I have challenges with is how the hell do you get the design and engineering community to buy into this notion, because it's a cultural thing. It's a serious responsibility to sign off airworthiness. And if you've been taught for 30 years, this is the way you do it, it's not easy to leap off into the wild blue yonder.
Absolutely. Yeah, that will be a challenge. Deep ingrained safety margins that aren't necessarily based upon reality, right? It's just estimates.
Well, they're based on a reality of experience and the fact that we don't know what we don't know, and therefore we have to have margin to manage that ignorance. That the introduction of software-enabled systems means that we can know. So you have a knowledge-informed approach versus a ignorance-informed approach.
Yeah. Well, John, this has been awesome. I've loved learning about you guys, your company. You guys are great. If folks want to follow what you're doing, how best would they do that?
Well, I think www.piasecki.com is our website, and that's one approach. And then there's, I think the PR guys have us, in various Instagrams and other services. I don't get in the middle of all that stuff. I'm too busy on the.
Yeah, understandable.
Yeah.
Well, again, thank you so much. If you're ever at Colorado, let me know. We'll host you.
We'll do.
Great.
Okay. Thanks.
Thanks.